We have two cars. We're given that there are two cars. And these cars are traveling on straight parallel paths. So let's start out with car Y. We'll draw a car Y like so. And we're given the velocity as a function of time. So we can see the velocity is initially 20 meters per second. And then at some point, it slows down and the velocity is 0. We see the velocity starts at positive 20 and then it decreases to 0 and comes to a stop. Well, car X, we can see starts out with a velocity of 0. And car X, we see speeds up, and by the time this thing is over, the car is going 10 meters per second. Now, there's no information given about where the cars start relative to each other. So it could be that X is ahead of Y, or Y is ahead of X, or they're right next to each other. They're different straight parallel paths. They could be next to each other like they're drag racing. When we look at the graph next, we could ask ourselves, what are the things we can tell from it? Well, we can read velocity and time. The slope, by definition, is dividing the axes, and that is the acceleration, delta V over delta T. And the area, V delta T, has units of meters per second times seconds, which gives us meters, and therefore the area is the displacement. So now, what is the question? Which of the following is a correct claim about car X and car Y? X and Y travel in the same direction. Well, for that to be true, the velocities must be both positive, or they must both be negative. If one were positive and one were negative, they would be heading toward each other or away from each other. But we see that in this graph that they're all positive. Even though the car Y slows down to 0 the entire time, at the instant before it stops, its velocity is positive something. It's headed in the positive direction. And the same thing is true as X. So traveling in the same direction looks like that's our answer. But let's now consider the other answers. It's always essential to disprove the others. So between 6 and 7 seconds, we look at times 6 and 7. What's going on between 6 and 7? Well, there's something that happens. There's an intersection here. Mathematically, it's an intersection. But what the meaning of that intersection is that they have the same velocity. Well, you can look from the picture here. They could have the same velocity, not be anywhere near each other. So even though they have the same velocity, it does not mean they have the same position. In fact, there is no information given in this problem that could ever allow us to determine if they're ever in the same position. So this one is out. Now, this question is testing us. If this were a position time graph and you saw this, then that would mean they're in the same position. But it's not a position time graph. It's a velocity time graph. And we look at the change in car X's speed per unit time. So the change in speed per unit time, hey, that's the acceleration, increases as time increases. Well, let's take a look at that at X. Well, the acceleration is the slope. This is a straight line, which means the slope is constant. The acceleration is constant. The velocity, the acceleration of car X does not change. So that question is out. The magnitude of acceleration of car X is the same as the magnitude of the acceleration of car Y. Now, if we were to compare those, let's do the acceleration of X. Delta V over delta T. We ended up at 10. The velocity changed by 10 in 10 seconds, so the acceleration is 1. And if we do the acceleration in Y, we had minus 20 change. It went from 20 to 0, so 0 minus 20, and that was all over 2 seconds. The acceleration is minus 2. The magnitude is not the same. That's false. It's twice as large. Choice 1.